Hi, here we are discussing about a project design of low power analog integrated deep convolutional neural network. Here the convolutional neural network are becoming important in applications such as medical imaging analysis and portable diagnostic devices and the real-time edge AI, but their hardware realizations still faces the challenges of high power consumptions, larger area and circuit mismatches. So earlier the analog approaches have shown improvement in power efficiency and compact computations, but they are often limited by mismatch sensitivity, reduced scalability and use of only simple activation functions like a ReLU. Okay, to address these issues in the existing approaches, this work presented back-end CMOS analog implementations of CNN block in 45 nanometer technology. So this proposed architectures introduced a soft decision analog multiplier together with a signed sigmoid activation circuit, which improves the accuracy of computations by handling both positive and negative signals. 3x3 kernel multiplications array is also implemented to enable efficient convolution operations with reduced transistor usages and smaller area and minimized interconnections. This novelty of this work is the realizations of CNN computations in back-end transistor level analog design, which offers low power and compact integrations compared with the conventional analog designs, which performance is evaluated through the detailed comparisons of MOSFET count and power, area and delay between the proposed circuit and the existing 90 nanometer CMOS technology. Okay, so here the post layout simulations was performed in Tanner EDA tool under the process of voltage, temperature variations and validate the reliability of the proposed circuit. This results confirm that this architecture is well suited for energy efficient on-chip classifications and low power and real-time applications. Okay, so now we can verify the paper. So this paper is fully designed for the low power and analog integrated deep convolutional neural network. Okay, so here they are developed the analog multiplier concept. Okay, but in this paper it will have more complications to get the output in the CNN kernel multiplications. Okay, so here they are given a figure 3 architecture, that is a differential difference path. Okay, and the basic building blocks of sine circuit schematic, it will be used to count the measurements. Okay, so which means using this V count 1 and V count 2 we can manage the circuit with a positive or negative based multiplications of sine sigmoid. Okay, so using a two opposite voltage control signals with the V count 1 and V count 2, so which are supplied to the bottom source terminal of two cascade current mirrors. Okay, so given in the circuit. Okay, so here the figure 7 is a proposed architecture, the schematic of the proposed analog multiplier design. Okay, so here the sine control signals which will be used in this part. Okay, after that they used for the sigmoid sine circuit. Okay, so the two model it will be used. Okay, but it will be take a more number of transistors in this architectures. Okay, so here the sine sigmoid you can count it. Okay, so it will be available with 15 number of transistors. Okay, so here they are used for two sine sigmoid circuit here. Okay, so totally 30 transistors it will be used in this the proposed architectures, and additionally 10 transistors used in the control circuit. Okay, so here totally 40 transistors it will be used for this proposed analog multiplier. Okay, so we solve these problems and we reduce the number of transistors in these architectures, and we created a proposed novelty architectures, and it will be developed in Tanner EDA tool. Okay, so here this is a proposed architecture. Okay, so here we named it's called a soft decision multiplier. Okay, so this is a test bench of the architecture. Okay, so here we are forcing an input is 0.8 volt at 45 nanometer CMOS technology. Okay, so this is all the controller signal, and this is the input, and this is the input reference voltages. Okay, so here this is a schematic we have developed it, and this is a control operations, and this is a proposed multiplications operations. Okay, so here we totally reduce the number of transistors and we have 8 transistors in the proposed multiplier. Okay, and totally we occupied only 18 number of transistors in the proposed circuit. Okay, and after that we simulate this work in 45 nanometer CMOS technology. Okay, and this is the simulation results. Okay, so here you can verify that the simulation value, so V input, V count value, okay, and this is all the input. Okay, so here 0 0 means multiplication value is 0, 0 1 means multiplication value is 0, 1 0 also come with 0, and 1 1 means it will be come with the 1. Okay, so using this single bit multiplications, we plan for the kernel multiplications for CNN applications. Okay, that is the convolution part. Okay, so this is a convolution multiplications of kernel. Okay, so here we are applied a 3 cross 3 kernel multiplications. That's why we given a kernel 0 to kernel 8, kernel 0 1 2 3 4 5 6 7 8. Okay, so here we applied a coefficient is 101 and 101 and 101. Okay, using this kernel coefficients, we applied a multiplication model. Okay, you can easily change this multiplication value here. Okay, so what are the coefficients you are needed? Okay, so you can easily change it and you can test the multiplication part also. Okay, so here the input we given a constant same value, so input in1 and in. Okay, so two differential input will be used in this kernel multiplications, and this is the top model of the architecture for 3 cross 3 multiplications. Okay, so here this one output is, okay, so this is a simulation output. Okay, so if you are given a 1 in the kernel coefficients, okay, so it will be generated the this pulse based output. If you are given a 0 in the convolution output, okay, so it will be maintaining a constant value, okay, in the convolution output. Okay, and using this Tanner output, we measured the logic area of MOSFETs and power consumptions and delay. Okay, it will be compared and it will be given in a comparisons document. Okay, so here this is a file. Okay, so here this is a file, okay, for comparisons value. So here the MOSFET, it will be take for only 18 transistors. Okay, and this is a power results and this is a delay results. Okay, so this results, it will be compared using a comparisons document. Here this is a comparisons analysis of this project. Okay, so here we are used for single bit analog multiplier and 3 cross 3 kernel multiplications. Okay, so here this 90 nanometer, it will be taken from the base paper work, and this 45 nanometer is our proposed architecture. Okay, so here the single bit analog multiplier existing, it will be occupied 40 transistors in a single bit multiplier and 360 transistors in a kernel multiplication of 3 cross 3. Okay, so here we totally reduce this number of MOSFETs here. Okay, it will be come with a 18 transistors in single bit multiplier and 162 transistors in a kernel multiplications. Okay, and totally we reduce the number of power consumptions and delay, okay, and also for area. Okay, and this is a comparisons analysis chart. Okay, finally we written abstract document for this project, title, base paper abstract, improvement of the project. So here improvement to develop the soft decision circuit of analog multiplier along with a sine sigmoid using 45 nanometer CMOS technology, and to develop the 3 cross 3 soft decision circuit architecture for CNN kernel multiplication 45 nanometer CMOS technology, and compare the parameters in terms of area, delay, power. Okay, and here this one is for to reduce the minimizations of interconnections. Okay, and proposed title, proposed abstract. Okay, and related nodes of existing systems, disadvantages and circuit descriptions. Okay, everything given. Okay, so proposed systems and proposed related nodes and proposed architectures, and the kernel coefficients multiplications value and coefficient procedures and the general VLSI nodes. Okay, and finally come up with the literature review. Okay, and references. Okay, thank you.